Okay, last time we talked about regression problem. But what if our labels are not a continuous value, but for example, follow another distribution when we have, for example, only two possible values, for example, on, off, 0, 1, or others. In this case, we are talking about classification problem. Let's talk about this in detail. So we also have this similar example in this case. I mean, also the PT diagram. But now, instead of having the saturation line, we would like to have the different points for different aggregation states. For example, if we have steam in this corner and we have liquid in another corner, and in this problem, because we are talking about classification, we can say regarding our experience that the same we also have features. And in this case, we have a pair of features. That means we have as well as temperature as the pressure. But the labels, we have either it might be a liquid state or it might be the gaseous state. So, and that's exactly the difference between regression and classification problem. You can also consider different types of the labels. It might be, for example, ordinal, so-called ordinals values when you have some sort of sorted values, for example. They're also discrete, and the limited set of values this value can take, but it should have an order. And it might be also nominal value, but you basically do not have any order, for example, on, off, or it might be, for example, liquid, steam, or solid. Basically no order, just a list of values this label can take. Those are experience. The same way as we did it for regression problem, we also need to carry out data split. So it's important that we do not use the same data as for training as for the evaluation of the model. In this case, we will also randomly select some of the, let's use this color. For example, for test, we also randomly select, but in this case from both classes. And in the ideal case, and it should be also checked before you come to the training process, that the distribution in your test data sets is the same as in your training data set or in the general data set. That means the amount of the labels of each type in training data set should be approximately the same as in the test data set. So we finished this experience. We have our data. Let's talk about the task. So in this case, we need to predict a class in this, whether it's liquid or steam. And for this problem, we will use so-called binary classification model. Or binary classifier. Why binary? Because we have only two classes. Either it's liquid or not. If it's not liquid, that means it's steam. So we have either zeros or ones. And for example, we say 0 is for steam and 1 is for liquid. Or for example, let's say not steam and steam. As the ground as foundation for the classification model we will consider now, it's also linear regression. So it derived from linear regression, but with some sort of extension. Let's talk about what the problem, why cannot we apply linear regression for this to classify two states in this sample. So the problem is here because if we apply linear regression model, that means that our labels can take any value from -infinity to +infinity. And that's the problem because we need as output either 0 or 1. That's why it doesn't work. So that's why we need to apply additional transformation on the top of linear regression that we will get either 1, either 0 or 1. And this transformation for logistic regression type of model we are considering right now will be so-called sigmoid function. It has very simple equation. And it looks like this. So we have t as our input parameter, and we have our sigmoid function, where we have the values from 0 to 1 as output. So here's 1. And here we have from -1, here we have 0, and here we have 1, and further. So let's consider some special points here. So let's say we have a point here. That would mean that these points can be predicted as class 0. Any point behind this line will be predicted as class 1. Here it's also important to mention the closer the point to the infinity, so for the class 1, the more the point on the right side, the more the model is sure that these points belong to the class 1. And the opposite works for the class 0. So the more the point left, the more the model is sure that this point should be predicted as class 0. So we applied this transformation. So basically, last time we talked about the equation for the linear regression, and this now we just apply this sigmoid function, and that will be the model. So we have no additional parameters. We had the set of b parameters dependent on the dimensionality of our input features. In this case, we have the same parameters. The sigmoid function doesn't have its own parameters, and that's why it's the model, we can say it's hypothesis for the logistic regression we can use for binary classification. Let's talk about performance of this model, how we can evaluate whether our model performs well or not. For that, we will introduce our new cost function. For that, let's also consider two cases. First of them, if the label is 1, and the second, if the label is 0. So, if the label is 1, we can consider this as a metric for our classification. And if the label is 0, we can modify it a little bit. And now we discuss why we can use it. So let's also consider some use cases or some points. So first of them, let's call it true positive. So basically our label is 1 and we predicted it as 1, but it's not like the ideal prediction. And that's why, let's say we have y equals 1, so our label. And we also have the, let's say, probability that equals 0.9. So in this case, let's say it will be somewhere here, this point, so it's true positive. And now let's calculate our cost function. In this case, because the label is 1, we will use the first equation. And then the cost function, let's name it c, will have the following value. So we find this one, and it will be around 0.357. So far so good. It's not that large. And if we go further and we say, for example, that this probability, this value is higher, so in this direction, and we consider the case where it's like 1, and we put it here 1, so ideal case, then it will be 0. That means for these particular points, the loss function, the cost function will be 0. That is good. Like, let's say the less, the better in this case. Let's consider another use case, another point. So true negative. In this case, we have our y 0, and then we also have the probability, let's say 0.1. It should be somewhere here, say 0.1. And because we have y equals 0, we will use the second equation here. And now we will calculate the cost function. The cost function is like the function how we define the contribution of this particular point to our general target function. And then now we'll calculate it, and it will be 1 minus 0.1, and it will be around 0.105. In ideal case, if you consider this one, that the probability is 0, in ideal case for true negative, it will be again minus logarithmus of 1 minus 0, and it will be 0. So no contribution. So that's why ideal cases are ideal. And let's talk about some false, for example, false positive. And it will be here. False positive. That means that the model says this point is positive, so it should be class 1, but it falls predicted. That means in general it should be here. The label is there. And we have our false positive with epsilon equals 0. But at the same time, the probability that this point belongs to the class 1 is higher than 0.5, because 0.5 is here. And for example, let's say 0.6, so a little bit to the right. And in this case, we can calculate the cost function, and it will be minus logarithmus minus V0 minus 0.6, and it will be about 0.916. That means we have a greater value than in previous cases, and that's exactly how you can define whether these points classified correctly or not. The larger the value we have here, the less precise our classifier is. And now, to complete our cost function, we can just find a sum of both of the terms multiplied by these values, and those we can come to the so-called binary cross entropy. And using this binary cross entropy, because we can also find the derivative of this binary cross entropy function, we can also use gradient descent to find the parameters, as well as for linear regression. And in this case, that's exactly the target function we will use to optimize to find the optimal parameters B for our classifier.